Hello and welcome to today's educational seminar, Improving Old Concrete from the Inside Out. I'd like to share with you today that today's presentation is the result of over 25 years of research, study, and application of some products that will astound you. You're going to hear some information today that you've never heard before, and at the end of the presentation, we're hoping that will stimulate you to realize that there is solutions available for what you may need in your industry. We're very fortunate today to have two accomplished speakers sharing with us about how concrete can be improved rather than tearing it down and rebuilding. Our first speaker today is Rick Hamm, who is an industry veteran with over 40 years of experience in the concrete and masonry industry. Rick is also brought in as an expert witness for construction situations and is very accomplished in his field with the amount of experience that he has. I'd like you now put your hands together and give a warm welcome for Rick Hamm.
Thank you, Martin. My name is Rick Hamm. I'm a concrete and masonry contractor from Orange County, California. Been in business since 1977. I've actually been involved here at the World of Concrete for many years. I've taken classes here and seminars. One of the things that I look for when I select a seminar is I want to walk away with something that I haven't heard before. And I believe what you'll find today is you're going to walk out of the seminar hearing things that you've never heard before. We contract in the commercial, industrial, and residential areas from ground up to retrofit to rehabilitation, and are asked to look at slabs on grade, foundations, retaining walls, water retention basins, parking structures, structural columns, podium decks, subterranean poured-in-place walls, shotcrete walls, and caissons. Let's talk a little bit about post-tension repair. We're called out frequently to look at compromised or failing concrete and masonry structures. I will often look at parking structures with post-tension cables that have been exposed on the surface due to abrasion and wear, due to oxidation and corrosion. Either way, we need to detension the cables. The concrete needs to be removed around the cables. The cables need to be repaired and respliced. Rebar needs to be doweled into the existing concrete. We set it with epoxy. The existing concrete needs to be coated with a bonding agent. The cables need to be coated with a corrosion inhibitor. Then the section needs to be replaced with self-consolidating silica flume and polymer modified concrete. If you think about all of that, that's a pretty expensive fix. Let's talk a little bit about spalled concrete with rebar corrosion. We get calls to look at spalled concrete due to electrolysis, oxidation, and corrosion of rebar. We go in and we remove the concrete to expose the rebar. We then examine it to determine if the rebar needs to be replaced or just coated with a corrosion inhibitor. We dowel and pin the existing concrete with rebar. Again, we set it with epoxy. And then we re-pour the section with a high-strength cementatious product with bonding agents and polymers. Let's go into a little bit about surface delamination. We're asked to look at surfaces that are delaminating due to thermal cycles and de-icing. Depending on the severity of the damage, we will either remove and replace, or we will scarify, grind, and overlay. Columns, structural columns. We get involved with structural column failures due to weakened concrete, low compressive strengths, or rebar that's corroded. There are times where we'll encapsulate the existing structure with a new column. We'll rebuild the damaged section of the column, or we'll remove and replace the entire column. Retaining walls with water migration. We are asked to look at concrete and masonry retaining walls that are experiencing water migration and efflorescence appearing on the face of the structure. We propose to excavate behind the wall. We then stockpile the soil on site. We waterproof the backside of the wall and the top of the footing. We reinstall a perforated drainage system. We put a Merafi wrap there along with a gravel backfill. Then we backfill and compact the on-site soil behind that retaining wall. So if you think about all of these repair methodologies, they're expensive, and the client usually doesn't know that that's coming. So one of the first questions that our clients usually ask is, why is this happening? They think that once you pour concrete, you don't have to worry about it anymore. They don't realize that concrete and masonry is porous and becomes compromised due to environmental extremes and contaminants such as chemicals, sulfates, salts, carbon dioxide diffusions, abrasion, etc. The next question that I'm asked after I explain that is, what do I do when the same thing happens somewhere else on my project? I respond by saying, the repair I performed here will need to be done there next. Which prompts the last question that is usually asked, what can you do now to prevent this from happening again on my project? I've had to answer this question basically the same way for 45 years. We don't presently have a way to prevent rebar in concrete from oxidizing and concrete from deteriorating over time. However, based upon new technology from William Reed, I will be able to answer those questions differently in the future. To explain what I mean by that, I would like to introduce Alan Smith. Alan?
Thank you, Rick. My name's Alan Smith, and I'm excited to be here to share some information with you that I think is groundbreaking in the way it applies to exactly what Rick has just talked about and explained. A little bit about me and my background so you know where I'm coming from. I've been a contractor in Southern California for 40 years, mostly in the field of renovation. We've done over 35,000 renovation projects, mostly entailing different types of masonry, cement products. And I've also been a member of quite a few different trade associations, and one of the ones I was not only a member of, I was chairman of the whole trade association. I was actually fortunate enough to be able to be running their research and development department, and we actually contracted with California Polytechnic University at San Luis Obispo with their civil and environmental engineering to do extensive material testing. I was fortunate enough to be able to chair that advisory board. And what we learned from that with cement and water interaction really grounded me in understanding some of these issues that Rick is talking about that have really been presented a challenge in the concrete industry for centuries, actually. But one of the things I remember taking away was the principal investigator at Cal Poly, a gentleman by the name of Damian Keslikev. When we were doing all of our research and discovery, he said one thing that has stuck to me: unless you can take care of the capillary issues and the calcium hydroxide issues in cement, you're always going to have this degradation. Even though we're coming up with all kinds of superior products to add and help and reduce that, you still have these issues. So what I want to go over with you right now is answering some of Rick's questions, and I'm going to take you on a little bit of a educational of cement and how it's made and how it hydrates. It'll be review for some of you here that already understand a lot of this, but again, we need to start someplace, and then we're going to go through the motions of how cement's made, how it develops, the microstructure of it, so you understand how we can fix that. And we're going to go over some examples of that too. Understanding the conditions that lead to potential problems in new concrete. Most aggregate is stronger than the cement paste matrix itself. During mixing, shearing stresses are exerted on the cement paste, which tend to cause the water to separate from the cement particles, creating what is called the interfacial transition zone. I'll call it the ITZ. Please remember that. We're going to come back to that. ITZ. Free water in the mixture leaves by means of capillaries and pore spaces that are formed during the hydration process. Hydration is another word. Write that down. We're going to visit that. Curing requires water in order to maximize strength gain and density through the hydration system. When reinforced concrete is cured, the pore spaces allow penetration of water into the matrix, which can or will carry the salts, the acids, other degrading materials into the matrix. This becomes the electrolyte in which reinforcing steel and concrete is deteriorated. Now let's start out basically with concrete. On the left here you see clinker coming out of the manufacturing. It's red hot. It's a produced product. Then you see it in the batch plant down on the bottom right, and then of course up in the top right you see concrete coming out of the chute of a concrete truck putting on the ground. It's pigmented. It's getting ready to be tamped and be trialed out, and the whole system starts right here. Once this is down, we have the process of hydration starts. And let's kind of go over that. Hydration, as it says here, equals chemical changes. So basically what's going on is water in the mix design consists of a mixture of hydraulic Portland cement, which is ASTM C150, sand, rock, and water. The 5 principal compounds that make up the cement paste, when cement and water are combined, you don't have to remember these except for this last one: tricalcium silicate, dicalcium silicate, tricalcium aluminate, tetracalcium aluminoferrite, and calcium hydroxide. Write calcium hydroxide down. This is an important compound we're going to come back to. Of these principal compounds, calcium hydroxide, which makes up approximately 24 to 27% of all new cement compounds, is the most soluble. Remember that word, soluble. Calcium silicate hydrate, or CSH, which makes up the strongest, or approximately 60% of the new compounds, is the densest and the strongest. When all the ingredients are mixed together, you have aggregates, cement paste, void spaces, shrink cracking, and interfacial transition zones, or those ITZs, that make up the total cement matrix. Interfaces, shrink cracks, capillaries, transition zones are the basic microstructure and properties of all cement products. Now let's dive into this a little bit. What are these products and why it's important we understand these so we know what's causing the degradation and also to know how to fix it. We're going to start with the calcium hydroxide, also known as Portlandite. Portlandite is a rare oxide mineral, the naturally occurring form of calcium hydroxide. Is also the calcium analog of brucite. It was named Portlandite because the chemical calcium hydroxide is a common hydrolysis product of Portland cement. So when you mix Portland cement together, you get a lot of Portlandite, or a lot of calcium hydroxide, way more than you'll find in nature. Important bottom line here, Mohs total hardness 3. Write that down. It's a 3 on total hardness. We're going to come back and visit that in a minute here. Larnite is also the calcium silicate hydrate mineral of general formulation. Larnite also occurs as an altered mineral in the metamorphized limestone. It occurs in hydrated cement paste.
Mohs hardness scale is at 72 on that. Those are your 2 basic compounds that form hydrating cement paste. Now we're up to the Mohs hardness scale. Now a lot of you might not know what this is. Well, basically, Mohs was a German geologist that actually put this together to test the hardness of different compounds and minerals.
Calcium hydroxide is on the total hardness or absolute hardness, is a 3. And you can see down at the 72 level is where your calcium silicate hydrate. Huge difference from soluble at a 3 to very hard and strong at a 72. So our aim here is to make this calcium hydroxide into at 3 into more of a calcium silicate hydrate at 72. And that's always been the big challenge. And here's what we intend to do with that. Let's dive in here and take a quick look at what hydration looks like and the paths of deterioration and how this is all interconnected. You can see right here the little white lines around the aggregates, and throughout this matrix is the calcium hydroxide forming, and it forms like a freeway or a spider web throughout all cement mortar mixes. And specifically around the ITZs, you can see them, which is where anytime the cement paste comes up to some aggregate, you have a little void space that's created by the water separating, and the calcium hydroxide forms in there. It also forms in your shrink cracks, your micro cracking, your capillaries, your voids. And you remember, this is a 3 on the Mohs hardness scale. It's very soft, it's very soluble. You have a freeway of soluble compounds in the cement structure, and this picture clearly shows that. Here's an even closer picture. You got an artist's rendition on one side and a close picture of the other of aggregate with a very loose fitting, loose plated calcium hydroxide particles that are very open and porous next to the denser calcium hydroxide, calcium silicate hydrate particles that are much denser. Here's a great picture of a calcium hydroxide under a enlarged photograph, and right next to it you have your calcium silicate hydrate. Now the calcium hydroxide, you can see, is a very large, loose plate-like disorganized structure, extremely permeable, and the water can get down into that, especially if it's aggressive, and break down that soluble compound. And right around that you see the very hard, dense structure of a 72 on the Mohs hardness scale. So as this calcium hydroxide breaks down, it creates a freeway or a capillary system for aggressive waters to get into the cement to break down the rest of it and or surround the steel and start the oxidation process. So with that being said, what is the most significant factor in the long-term durability of concrete? Well, the durability of concrete is directly related to the permeability or the porosity of the concrete itself, as we were just talking about. Why? Because most of the mechanisms that cause the damage to concrete involve the diffusion of the reactive ions, such as salts, chemicals, by permeation or penetration, which attacks the cement paste itself, as we just talked about, or the steel reinforcement, or a combination of both. The ITZs, the capillaries, calcium hydroxide, shrink cracks are more permeable than that bulk calcium silicate hydrate, as we just saw, and in turn will make the concrete much greater in permeability. What's the solution? Well, let's enter the microstructure. Let's take a close look at what's going on inside of this cement matrix in the microstructure. We are going to enable what we call the new technology. Okay, now we're going to enter the microstructure of what cement looks like deep inside the capillaries and deep inside the microstructure itself. Because this is where the degradation happens and this is where the healing happens. Now, when I started getting into this cement research years ago, I realized that the cure for this was getting hardeners down into the deeper part of the cement matrix, but we had a big problem. We had a particle size issue. The hardening agents, the silicates, is like a soccer ball, and getting down into the pore structure is like chain link fence. And to get a soccer ball through that is very difficult or impossible. And that's what I thought for years until I was introduced to this new technology. What we call OXOCRETE, this new technology, is derived around an incredible out-of-the-box thought process of dealing with particle size issues by attacking the water molecule with a very interesting charging system where we go after the acidic side of the hydrogen atom as well, and creates a whole different environment to be able to bring silicates deep inside of concrete. And I really can't say much more just because of proprietary requirements on that, but we have to kind of keep it light on this. But what we do is we really alter how water and the delivery solutions work in concrete and able to get into them. I'm going to explain to you exactly now how this happens.
The OXOCRETE CPR1 is the first device we're going to have that goes into the concrete to stop this. And what we're seeing here is newer concrete that started having issues right away. And when it starts happening, I know it only gets worse. There's a permanent solution to stop that problem now, like Rick was talking about. So let's dive right into that right now and see what this is. So the mechanisms, how OXOCRETE works. What's this new technology? Well, we start off with raw concrete and we apply a process called OXOCRETE CPR1, followed by OXOCRETE CPR2. And then we have an altered concrete matrix. So it's as simple as this. We're spraying on what we call charged solution onto a deteriorating concrete surface. This process can go 1, 2, 3, 4, 5, 6 applications to get this penetration into the concrete with this solution. Now, how does this solution work?
Well, the OXOCRETE CPR1 works on the acidic side of the hydrogen atom. The acidic side of the water molecule, once penetrated into an alkaline material such as concrete, looks for a highly alkaline substance such as calcium hydroxide, and it forms a micro solution of the same part. So it's basically a broken down calcium hydroxide. And this sets the stage for the next application to create a reaction product. Okay, we're looking to change this into something different. So here you can see the capillary systems that are enlarged and micro cracks and microstructure of some deteriorating cement. The lower pH of deteriorating concrete or low alkalinity is part of this that draws in our charged solution. And you can see I have some brown dots in here that represents the steel in there, and that's surrounded by deteriorated concrete, and you have oxidized steel. So what we do is we put our CPR1 on the surface, and the low pH actually draws this, we'll call it a primer fluid, down for the full thickness of the deterioration. Now, if you only have 1 inch thick of deterioration, that's about as far as it'll go. But we've got it as deep as 8, 9, and 10 inches into concrete for that full saturation into the deteriorating concrete with this primer fluid. So, CPR2 is basically our product or liquid product that has a charged water on it that's different than the first one, than the CPR1. And now this is sprayed on in multiple applications to what we call the point of refusal. Now, how does this get down into the concrete? Well, just like the first one, CPR1 we put on, we spray the CPR2 on, and the primer fluid, which is a charge to it, pulls the secondary fluid into it to the full penetration, and this contains the silicates. Now this is getting that soccer ball into a chain link fence by the draw, or as it's pulling it, it's actually able to squeeze it in and pull it into the full depths. The increased pH is achieved throughout the full penetration, which is absolutely spectacular, never been done before, and this is what's so groundbreaking about this. And it can pull in that full saturation thickness by drawing particles and squeezing them down through into this low pH is the draw. So as it goes down, you can just see this blue turning purple, and it inducts it down into it. And it surrounds the steel, it surrounds the aggregate, it surrounds any place where you had deterioration before, and filling them with a silicate, and in essence turning the calcium hydroxide into calcium silicate hydrate all around the void spaces, which is going to basically strengthen the whole matrix, harden it, and create a completely different cement environment. So what's happening here? That first charged acidic water forms an alkali solution. OXOCRETE solutions that are charged comes in, and it looks for that acidic solution and penetrates and pulls down. And that calcium silicate hydrate is formed where it used to be the soft calcium hydroxide, creating a hardened surface up at the top and an aerosil gel deep within the matrix. Now, how do we know all this? This is a lot of great information, but how do we know this is true? Well, let's go over that. We're going to talk about testing results. We're also going to talk about some historical evidence that really shows how this works. Okay, let's start right off. We have some restoring the pH to better than new conditions. So we have a core with the tape measure on that's about 7 inches long that was taken out, and we had phenolphthalein was put on there, and that actually can tell you the pH measurement on that. And this older concrete that was degraded had a very low pH, which shows that there's hardly any color or purple on that. The cores on the right were taken a year after the OXOCRETE system was put on. The post-process cores were taken after 1 year of exposed to citric acid, and a citric acid exposure throughout the concrete area was constant on some tipping tables. Note, the phenolphthalein is used to determine the pH of concrete and the core materials. The ones on the right are extremely purple because it means that the pH was raised on everything to as good or better than new pH levels. So it shows the full penetration of our product. The core on the left, the picture of 4, was 7 inches. Let's take a better one look at this, the depth of silicate penetration. There's different application here, a different facility. The one core on the left was basically had no purple. That shows you had a very low pH. After it was treated, I believe this was an 8-inch core. Full penetration, you can see the purple shows that the silicate, which will change the pH from low to high, had the full penetration all the way down. Now, that's on the outside of the core. How do we know what's happening on the inside of the core? Well, here's a test where we did 6-inch cores. We took 6 1-inch slices out of them and basically ground each slice up into 1/2 inch minus, put it in distilled water, and let that water react and test the pH. And so that's what we did. We left them in there for about 20 minutes. And the untreated had pHs of 7.5. The treated side went to 8.5, which is a 12% increase in only 20 minutes on down the line, from a 12 pH to a 14, all the way down to the very bottom, where it went from 7 to 9 with a 23% increase. So within 20 minutes of just testing those crushed up samples, we saw this dramatic increase in the pH, which just shows complete silicate penetration, which is extremely exciting. And I don't think there's another product out there that even does anything similar to this at all. So the other way we're testing is, of course, with the compressive strength, or PSI testing. And this is really where you know if the job is working. Did your concrete get harder all the way down for the full depths? Well, right here I have a chart of some jobs that have been done. Of course, there's hundreds of jobs that have been done with this already. You might not know that, but this product's been around. As you can see, the year of 1992 was a church called St. Paul's Church down in Key West, Florida, 150-year-old church that had segments of the cement structure, which was made out of beach sand, if you can believe it. I had 650 PSI. After 28 days in our process, it was up to 1,440 PSI, 122% increase in PSI, 122%. 2 years later, St. Paul's Church called us back out again to do another section, which had an 850 PSI, and we got it up to 2,500 PSI, 196% increase in PSI strength. This is amazing. As we go down the chart, and then we had a residential home that had grade beams that had only 930 PSI that we took to 2,320, an incredible 149% increase. This is stuff you don't see anywhere else. Mulberry phosphates, which is a phosphate plant, very terrible environment for concrete. And we had 57, 60s, 50s increase, saving that from having to be torn down and replaced, just like the church. The only thing that church had to do up in Key West was to have to be destroyed or be fixed like what we did. And so we're saving the complete destruction of these structures and facilities. And as you go down, you can see similar results all the way down. The results started a new era in concrete restoration. Let's go over some historical case studies, anywhere from 4-year-old all the way to 25 years old. Now, we just talked about this church, 150 years old. This was, we can consider it antiquity. There's a lot of old churches around in the world that are failing and having this cement microstructures start to degrade. And again, here's where we started at 650 psi, 121% increase. Again, this is unbelievable. Such are the achievements of age structures in various types and conditions. You know, the results attained then, which are all certified through ASTM engineered certifications, stand alone today as living proof of performance. This church is still there today, strong as ever. Here's some balconies. It's called siesta breakers. You can see this is a 6-story balcony on a high-end condominium complex in southern Florida. A lot of the testing and a lot of this application was done in southern Florida, where William Reed, the inventor, was a contractor, and primarily his influence with this product was there over the years. He really never got it out and marketed it much, but he really just used it off the referrals of the local engineers. He had over 23,000 square feet of parapeted balconies that were in complete distress. The steel was oxidizing, it was blowing the concrete apart, and it was either tear those decks out or actually save them if we could and try to modify them and rehabilitate them the best we can. So basically the results were of our process was we actually had the pH came back up to fully restored. The increase in compressive strength was over 30%. We stopped all the steel from rusting. We actually had it so strong we could put an overlay on it that would stick. It's lasted to this day without any more major repair. The average job of this caliber, of this type of repair, goes about anywhere from 4 to 6 years before it needs another full repair cycle on this. We're able to save this, coat it, and no more repairs are done. It's been over 24 years. I saw this for myself. It looks like new, still to this day. Mulberry phosphates. Phosphate plants are notorious for being aggressive on cements. We did a full facility there. We restored the alkalinity in the concrete matrix. We increased the concrete compressive strength. We actually diminished the absorption and permeability in there. We filled up all the capillaries and we stopped the problem. So here's a picture of what we did there. The OXOCRETE application on some of the worst forms of deterioration like this. Before and after cores were taken for certified engineering analysis to see what would happen. And what happened is basically due to OXOCRETE treatment, the alkalinity was completely restored. The average compressive strengths were increased by 48% over the original test averages. Full penetration was 5.5, and partially some places almost to 7, as defined by compressive strength and microscopic examinations. So this was a very successful, as all of them are. Tropicana tipping tables. This is where Tropicana has citric products with a lot of citric acid, and there was a lot of degradation in the concrete throughout that, and that was completely restored back to the original design strength. You can see all the pitting and aggregate loss due to citric acid exposure throughout this, down in this vault, complete deterioration, and that was completely finished. The whole tipping tables were brought back. The results were the concrete pH was fully restored to like new condition, saving from having to tear it all out and replace it. Resists attack from the water products, so the citric acids from the fluids there stopped destroying it anymore, and it's just basically an overall success. On and on and on with these. We even get into the infrastructure of wastewater treatment facilities. We're retaining walls, surfaces above the water line from hydrogen sulfide attack. All the surfaces were cleaned with one of the OXOCRETE products, and then shot with the OXOCRETE before and after the repairs were done on it where their cement was missing. And then a product called LiquiSeal was applied after the final application of the OXOCRETE systems completely restored, saved from having to tear the walls out, and this infrastructure was saved. Another very interesting case history is these foundation slabs for a home in Florida were poured, and unfortunately the delivery truck brought in 3,500 psi and 5,000 was called for. They didn't realize it till after it was poured. A couple days later, Hurricane Irma blew in and submerged the whole thing in salt water. On top of that, you can see the trees are all shredded. So you had underperforming or understrength concrete and then saturated with salt. Well, the original cylinders came back at 3,500 psi. It needed to be at 5,000, and that was a big problem. And what can you do? So they called in our technology to see what we could do, and the results were, and here's a quote from Robert Samara. He's an engineer, and this was his own personal property. And this is a more recent project requiring concrete intensification occurred on his own personal home being built in Marathon, Florida. On-site batching was improperly done, and the 28-day test results show the maximum strength of the foundation system of only 3,500 psi for a 5,000 pound mix call out. So Robert called William, and he described the problem, and instantly he came out that week, intensifying 600 lineal feet of foundation grade beam. Tests were taken the following day and already had a 400 psi increase in concrete strength was noted. Concrete tests were taken 28 days later, and the maximum strength of the concrete was 5,200 psi. This process saved the contractor and the concrete company thousands and thousands of dollars of tear out and replacement, and eliminated a delay in the project. He says, I'm very happy with the results and was able to continue with the construction. I've also specified the resurfacing and restructuring process for a project called Ocean Reef in Florida for 6 buildings with severely damaged foundations and grade beams using this process. Without it, the buildings would have to be either extensively reconstructed at the grade beam or even possibly torn down. And let's visit that project. And what that is a very high-end condominium complex where you can see the grade beams are completely deteriorating, where the steel has been completely saturated, it's oxidizing, it's blowing out the cement, and this needs to be repaired immediately. So the deteriorating grade beams with oxidizing reinforcing steel. As a matter of fact, it was everywhere. If you get cameras inside, underneath the foundation, you see throughout the whole project, you had deteriorating grade beams. So what did we do to fix that? Well, we did our process like we explained earlier, and you can see here the compressive strengths in 80 and 90 days were off the chart. The average increase was 42%. All corrosion of the existing reinforcing steel embedded within the matrix of the 30-year-old concrete ceased to exhibit further corrosion. So not only does this stop it, it keeps it from rusting anymore. So that's a big win, and it's permanent too. We're going to show you that in a minute. All testing was engineered certified on site and in laboratory conditions in accordance with ASTM standards. So we basically saved this condominium complex millions and millions and millions of dollars with this process. Next thing is the Wells Fargo Ellis Building, Sarasota, Florida. Another great project. Lots of parking structures that are deteriorating all over the world. The aged parking garage had cracking, minor spalling, and leaking into the first level bank area. Not good. We came in and treated it with our system, made it like new, that had the Oxycrete treatment put on it. And the overlay shows no signs of wear, even on the 180-degree turns and the 30-degree ramp incline. The superior densification capacity and the application is clearly evident on the overlay treated here. Now, how do we know how well it worked down deep? Well, we actually have what's called a profimeter, the ProSec brand, corrosion testing, and we tested throughout our application to see if there was any further rusting of the steel, and it showed that all the steel had ceased from oxidizing anymore. This is a great instrument to use. I highly recommend it. So, a quote from Robert Samara, the engineer of record on many of these projects. He says, I have been a licensed engineer for more than 40 years and have specified and utilized many different concrete restoration and intensification processes and products. The most effective system I have ever encountered and used is the OXOCRETE process offered by OXOCRETE Systems. It's previously known as microcysts. The OXOCRETE process has provided successful results in the field application for more than 20 years, saving property owners significant amounts of time, expense, and process. So not only is this new technology that you're hearing about that's being introduced to you now, it does have a track record over 20 years utilized in the field that we're bringing to you now with both testing and field application. So, OXOCRETE is a non-destructive concrete restoration product that can be used anywhere. Why wouldn't you use this product on any cement application? Even on new, putting this on helps strengthen it. Or if it's getting older, even if it's starting to age, do it sooner than later. But if it is in those stages where you're having a lot of deterioration and big concrete repairs, it can be used to save that. The OXOCRETE process is designed and functions as an internally penetrating concrete restoration system, like it says on the title, from the inside out, by the use of specifically processed solution in combination with a precisely manufactured reaction agent. New and old concrete substrates can be permanently altered in a non-destructive manner. This process has been tested and utilized in many various projects throughout its history, as you can see, with long-term empirical results. The primary results of the process application is the reduction and elimination of reinforcing steel oxidation or rusting within existing aged concrete structures, the increased compressive strength in both newly poured and aged concrete. So important to get that strength back. The restoration of alkalinity or pH to better than new. No further deterioration after 25 plus years from application of the OXOCRETE product. This is fantastic news for the cement and infrastructure industries that need to be repaired in a non-destructive manner. So, OXOCRETE, it's trusted for antiquity. It strengthens our history, as you can see. All over the world, this can be used to save our decaying history in a very, very efficient manner. OXOCRETE equals almost total hardness of 72, rehardening and trusted for use in infrastructure restoration worldwide. Very important, OXOCRETE is trusted for our nation's most sacred monuments. In the United States, we have the Veterans Administration, and throughout their cemeteries, they use this for these headstones, not only clean, but to preserve something as sacred as this. They trust the OXOCRETE product to restore these things. And with that, I'd like to hand it over to Martin. Thank you very much.
Well, thank you, Alan, and thank you, Rick, for your insights today and expertise on this amazing new technology. We heard Rick share a little bit about the problems, the pitfalls, the challenges that he encounters as a concrete professional. And then we turned it over to Alan to kind of explain the science behind it, of this amazing technology that is supported by years of testing, case studies, and as you saw in the examples that Alan shared, there's multiple projects where this has been used to save concrete. So in addition to these amazing benefits that are offered by this product, the clincher for this is that it's clean and environmentally safe. It's green. And in our world today, we're aware of, in our environment more than ever, we see every day how destructive it can be on our planet. And concrete destruction and takedown is quite a messy job. As you can see from this picture here, there's a lot of dust. That dust is filled with toxins, other things that impact our health and our environment. The landfills that we have are filled with concrete, or can be filled with concrete that can take up landfills and takes a long time to dissipate and go away. So there's a real negative footprint from concrete destruction. So then we turn over to a product like this that has all the benefits that you saw, but it's also green. It's the solutions that we're using and the processes are very clean, natural, and there's no toxins. I mean, you can literally drink the product. It's that safe. It has the recognition of GRAS, which is generally regarded as safe. So there's a lot of benefit, and there's also a very safe solution there that it helps us as we strive to protect our planet. The other big thing is with a product like this, you don't have all the downtime. You don't have the business interruption. You don't have road closures. The revenue is not compromised because of the time it takes to do something like this. This process is very streamlined and the footprint is very minimal. So once this product is applied, it's almost immediately available for access. And as I said, you don't have to shut down an airport. You don't have to block a road and so on. So it's very good that way. And as part of our efforts that we're all part of here in our world here in America and around the globe to do what we can to make sure that our planet is not sinking into degradation and falling into disrepair. So this is a great product that helps us heal our planet. And as I said, it's earth friendly. It allows us to all come together and do something that is helping our planet and saving costs. It's an earth friendly product.